then is next says also this is the root test, ratio test. Third test is ratio test. Let x, which is x n, be a sequence of non-zero real number. Real numbers. Then the first says if there exists an R, if there exists R belongs to the set of real number capital R with 0 less than R less than 1 and k belongs to n set of natural number n such that mod of x n plus 1 by x n, this is less than equal to R for n greater than equal to k, then the series sigma x n 1 to infinity is absolutely convergent. And part B says if there exists k belongs to the set of natural number n such that mod of x n plus 1 by x n is greater than or equal to 1 for n greater than equal to k onward, then the series sigma x n 1 to infinity is divergent. Again, as a corollary of this result is the limiting variable. So, again we say the corollary to this is let x n be a sequence of non-zero terms. If x n be a non-zero sequence of real numbers, and suppose that the limit exists, limit of mod x n plus 1 over x n as n tends to infinity exists and say R, then the series sigma x n 1 to infinity is absolutely convergent when R is strictly less than 1 and is divergent when R is strictly greater than 1. Again, for R is equal to 1, test fails. Okay. So, now if we look this thing, then for R equal to 1, the testing fails. Okay. Now, there is another test which is known as the integral test and which is very powerful test, but of course, it requires a knowledge of the Riemann integral function, but here we will assume f is an element in the Riemann integrable function. Riemann integrable function we mean that suppose a b is an interval. Okay. A b is an interval, say here when we divide this a b into the partition and then finding the sum of this, then a to b f d a can be written as the limit of the sum of this. So, this we will discuss it when we go for the Riemann integral chapter on Riemann integration, but let us assume the f is an element of the Riemann class of Riemann integrable functions, where the integral test help. So, we are interested in the test right now. So, third test is, or fourth is the integrals test, which is very powerful test. Okay. So, here we assume let f be a positive. Now, one more thing is concept of the improper integral. So, here let f is an element, or let us take what, let f be a positive decreasing function on the set T, where the T is greater than or equal to 1. Then the series sigma f k, k is 1 to infinity, converges if and only if the improper integral improper integral 1 to infinity f t dt, if the improper integral which is limit 1 to b f t dt b tends to infinity exist. Okay. In case of the convergence, the partial sum Sn of the series sigma f k, k is 1 to n, the partial sum means k is 1 to n, f k, and this is k, okay, and the integral and partial sum this and the sum s and the sum s, which is sigma f k, k is 1 to infinity, satisfy the estimates the inequality integral n plus 1 to infinity f t dt, which is less than equal to s minus s n, which is less than equal to n to infinity f t dt. So, what this result says is that if f be a positive decreasing functions on this interval, on this set t, where t is greater than equal to 1, the series sigma f k converges if and only the corresponding improper integral exists. So, basically the integral sets test, it connects the convergence of the series, infinite series, with the improper integral. So, here we are having the two terms, one is the improper integrals, another one is the of course, that Riemann integrable functions. Now, what is this improper integral? Let me, before going for the proof, let me see the first, the improper integral. Improper integral. Improper integral, if suppose the function f, which is defined over a certain interval say a b, then a to b f t dt. If f is a continuous function, then this integral is known as the definite integral, which we know definite integral, is it not? If f is a continuous function, then a to b f t dt represents the definite integral, and it is known as the definite integral, and it represents the area bounded by the upper bounded by the function y equal to f t and below by x axis and a to b two ordinates. Now, if one of the limits is infinity or minus infinity, then such an integral we call it as an improper integral of the first kind. If either a or b or maybe both, one of the limit either a or b is plus infinity, minus infinity or maybe both, then the integral is known as improper integral of first kind. Now, once we have one of the limit as improper integral, that is integral a to infinity f t dt. So, this is improper integral of the first kind. Now, whether this integral converges or diverges depends on the limit of this. What we do is we consider a to b f t dt and then take the limit v tends to infinity. Now, if this limit exists, then we say this improper integral converges. Now, if this limit does not exist, then we say this improper integral diverges. Similarly, minus infinity to alpha, we can in a similar way we can say define the convergence or the divergence of this improper. The improper integral of the second kind are if a and b f t dt is given, but f is not continuous. Suppose it has a point of discontinuity over the interval a b, then such an integral is not defined basically over the whole interval a b. Say for example, if I take the improper a to or 0 minus 1 to 1 dx by x. Now, this integral function f x is 1 by x is not defined at x equal to 0. So, it is an improper integral of second kind. Clear? So, these two types of improper integrals are, one is the improper integral of first kind, another is the improper integral of second kind. Now, here what we are assuming is improper integral of the first kind. So, if a series is given and the function f is such which is of decreasing nature over the interval 1 to infinity, then the nature of this series sigma f k converges if the corresponding improper integral will exist. Clear? And of course, vice versa corresponding. So, this rates the convergence of the series with the improper integral, and that is why it is known as the integral test. It is very powerful test, one can derive the earlier test with the help of this integral test. So, let us see the proof of this result. So, we go to the proof of this. Okay. Now, it is given that function is decreasing since f is positive and it is of decreasing nature and decreasing on the interval over the interval t is greater than or equal to over this set. So, we can take the interval say k minus 1 k. This is interval function is decreasing over this interval k minus 1. Then we have obviously this relation that f of k is less than or equal to integral k minus 1 to k f t dt, which is less than or equal to f of k minus 1. Since the function is decreasing, the largest value will be attained at this point k minus 1 and lowest value will be attained at the point f k. What is this value? This is the area represented by this. So, basically the functional value between k minus 1 to k. So, this will be the portion in between these two. Okay. Now, let us take the sum. So, take the sum of this, take sum over k when varies from 2, 3 say up to n. Then what happen? When you take the sum of this k, then it is sigma k equal to 1 to n is the S n. So, we can say S n minus the first term f 1, right hand, and this is k equal to 2, 3. So, 1 to n f t d t, which is less than equal to, when you write the sum of this, it is S n minus 1. Okay. So, we get this. Now, from here say star, what we say, the nature of this limit of this integral will depend on the limit of S n and vice versa. If the limit of S n exists, the limit of this will also exist. If limit of this exists, limit of S n will also exist. So, this shows that this implies the both or neither of the limits exist, both or neither of the limits S n as n tends to infinity and limit as n tends to infinity 1 to n f t d t, both will exist or both will not exist. That is one thing which you. Now, if they exist, then add them. So, then add this say this part from here again, let it be a, then sum is a for k is equal to n plus 1 to m, where m is greater than n, sum of this. So, when you sum up this thing, what happen? This is k equal to m to, so S m minus S n. So, this will give S m minus S n, which is less than equal to n to m and f t d t, which is less than equal to, again when you sum up this thing, that will be equal to S m minus 1 minus S n minus 1. So, that will be there. Okay. Now, from here, so this implies that. Now, if I take m integral of this, say suppose I replace n by n plus 1, m by n plus 1, then what we get? N plus 1 to m plus 1 f t d t. This is nothing but what? When you write m equal to m plus 1, n equal to n plus 1, this is less than equal to S m minus S n. But S m minus S n is also less than equal to this integral n m f t d t. Okay. Now, clear? Now, from here take the limit as m tends to infinity. So, take the limit when m tends to infinity, fix n by fixing n we are not touching. Then what happens? When you are taking the limit, you are getting n plus 1 to infinity f t d t. F t d t is less than, when m is sufficient, this will go to S. So, S minus S n, this is less than equal to n to infinity f t d t, and that is what the result says. The result is this, is it not? So, we got the result for it. Okay. So, this proves that. Now, let us say application part. Suppose I take how to apply of this result. Let us take this series. We know the series sigma 1 by n to the power p 1 to infinity converges if p is strictly greater than 1, diverges if p is less than or equal to 1, because equal to 1 it is a harmonic series. Now, this can be proved, it can be shown with the help of integral test. How? Let us consider that what the integral test says. If you look the integral test is this, that if you want to find the nature of this series, write down the corresponding integral f t, and then if the limit of this exists, then corresponding integral will converge. So, this will be taken like this. So, consider integral 1 to n dt over t to the power p. Consider this integral, because we want the sigma of this thing. So, f t is 1 by t. So, 1 by n p, and then this will give 1 minus 1 by p, 1 over n to the power p minus 1 for p different from 1. Now, if p is greater than 1, if p is strictly greater than 1, what happens? The limit of this as n tends to infinity 1 to n dt over t to the power p, this will, when p is greater than 1, this will remain positive, power is positive, it will go to 0, and we are getting basically 1 over p minus 1, a definite number. So, it converges, exist, instead of this exists. Okay? And if p is less than 1, this will go in the numerator. So, it will diverge. So, it will go to infinity, that is does not exist. It means the corresponding series, therefore, the series sigma 1 by t to the power p, instead of t we can write n to the power p, n to the power p, n is 1 to infinity, converges if p is greater than 1, diverges if p is less than 1. And for p equal to 1, obviously, it is a harmonic series. So, we can get this result quickly. Okay? So, that is what we are getting. Now, there are few more tests which are known as the Ravi's test, and of course, the Ravi's test we will take up in next time. Then, okay, thank you very much. Thanks.